start slowly. It takes, based on this morning, it'll be about an hour and 10 minutes. Again, I'll probably do most of the talking. And this is fundamentally lesson 4 is review of pipe flow principles from fluid mechanics. And it's just that. It's a review. So let me get darn messages telling me how they can help me, and they really can't. So in the lesson collection, there should be lesson 4. There is, and there's not much in it. There's basically a link to this web interface. So before I continue, so I'll ask my question. Can you hear me? Yes, okay. At least one person can. I consider that enough. What that means, the audio is being picked up, so at least on the recording, you may have to turn the volume way up, but it will capture it. Actually, is the recording running? Yeah, it is. Okay, so this is lesson 4, and I've entitled it Pipeline Head Loss Models, and we're going to review pipeline head loss models. So these are the models that are used to compute the losses in pipe and other components of a distribution network. That in turn manifests itself as pressure drops as you move throughout the system, and the information is ultimately combined to assure that the proper pressure in the system is maintained. I have to go away from the video for 1 minute, so I'm just going to leave it running, and I will announce when I get back. I have something in the backyard I got to deal with right now. I'll feed you guys in a little bit. All right, I'm back, and I apologize for that, but I had an animal in the backyard and had forgotten about it, and he needed to come into the house. So everybody's in the house now. Picking up where I left off, review of pipeline head loss models, and the video links, none of these are available right now or working. I don't have this pre-recorded. So today's video will replace one of these. There's also a video from the morning section that will replace one of these. And in data links, there's nothing in supplemental data, but Spreadsheets has some examples of what I'll talk about today, although I won't necessarily go through the spreadsheets, but they're there if you want to explore them after reading today's materials. There's also links to reading materials, water distribution system, which we visited last time, notes on hydraulics. So these are my notes from 7 years ago of what we're talking today, and let's see how far they go. Actually, they get pretty far. None of the spreadsheet stuff is relevant anymore, but these notes will supplement what I'm talking about today. And closed conduits from Chin's book called Water Resources Systems discusses the mathematics and the background fluid mechanics theory for pipeline systems, and I'll leave you to read that at your leisure. And then the last one I have is Chapter 5 from Robertson and Crow, which was my hydraulics textbook in the 1980s. It's a while ago. And it has a whole chapter on closed conduit flow, and I would strongly recommend you take a look at this because it pretty much has everything one would need to know for the hydraulics of closed conduits as well as networks. Part of it that is obsolete, I'll show you. I guess technically it's all obsolete, but the part that's especially obsolete is the network portion. And what's obsolete about it is the method of solving network systems. So that's not obsolete. We're actually going to visit this exact example in a future lesson. Same with that example. I don't discuss manifolds in this class, but scrolling down until hopefully you're good and nauseous now. Networks, the methodology discussed here is probably not used anymore unless you're doing them by hand, and I will demonstrate a better way to do them by hand. By hand I mean scripting it into an R script or programming it into a spreadsheet. And we're going to use commercial grade software anyway. Okay, so let's move on with lesson notes, and we'll look at lesson part 1. So, Pipeline Hydraulics, Part 1, Fall 2020, CE 3372. And I know you can't see it because I don't have the video on, but we have a special guest for this lecture, Nico the cat, who is an expert in cat hydraulics, which means the ability to squeeze into and sleep in places that are unimaginable. So I'm going to tolerate him because currently he's not sitting on the mouse and he's not sitting on the keyboard, which is quite rare for a cat when you're busy at the computer. So we'll start the review off and review some things about flow characteristics that we would have had in fluids mechanics class. So the main characteristic to remember is that water moves from high to low energy, and the path it takes will be the path of the lowest resistance. In other words, as far as we know, it tries to maintain the energy that it has. The metric that we use for energy in water systems is called head, and it's the energy per unit weight of a fluid. It has dimensional units of a length. So head is expressed in lengths like 30 feet ahead, 50 feet ahead, 10 meters ahead, and so forth. If we need to move water uphill or get over some kind of barrier or overcome excessive frictional losses, the tool is a pump, and they are used to add energy to the water for those various purposes. A gravity flow system is a system where all the energy that's required to move the water from the source to the user is provided by change in elevation. So in other words, water is stored on the top of a hill and the users are at the bottom of the hill. That would be a gravity flow system. In instances where that cannot be accomplished, we have to provide some other driving force, and it's usually done by pressure, and those are called pressure flow systems. Most real systems are combinations of the two. The volumetric flow rate is the amount of water per unit time that passes a cross-sectional area. In fluid mechanics, we usually use the symbol Q, but it can be any letter of the alphabet that you like, as long as you define it clearly for the reader. And if we are to divide that volumetric discharge by the cross-sectional area of flow, the result is a object called the mean section velocity. And the mean section velocity is different than a point velocity, but when someone talks about the velocity in a pipe, most of the time they mean the mean section velocity, or they mean the discharge divided by the cross-sectional flow area. Profiling the flow in a pipe is not an easy task, and it's not done frequently in municipal systems. That's more of a fluid mechanics issue. At that point, those are point velocities. When we're discussing the velocity of flow a certain distance from the center line of the pipe, that's not going to be a mean section velocity. The mean section velocity would be the area-weighted integral of that. The next concept to refresh our memories is the concept of continuity or conservation of mass. And in this drawing, we have two pipes that are connected to one another. The one on the left is larger diameter than the one on the right, and there are no leaks in this system. Thus, the conservation of mass statement is that the discharge in the left portion, Q1, is equal to the discharge in the right portion, Q2, so the Q doesn't change. That implies that the product of the cross-sectional area on the left section and its mean section velocity is equal to the product of the cross-sectional area on the right and the mean section velocity, or as written here, A1 V1 equals A2 V2. Another type of implication of continuity is the continuity at a junction. So a junction or a node, the words are often used interchangeably in hydraulics, is a location where two or more pipes come together. So a three-pipe junction is shown here in the drawing. And in the three-pipe junction, this left portion has discharge Q1 coming into it. This upper portion has discharge Q2 leaving the junction. The lower portion here has discharge Q3 leaving the junction. And there is this other discharge leaving that I've labeled D for demand, also leaving the junction. So the demand represents water that leaves the pipeline network and goes to customers. And that's the normal convention. And by convention, demand is considered positive leaving a junction. So if we were to write the continuity equation for the junction, which is this dashed object here, we could write that Q1 minus Q2 minus Q3 minus demand equals 0, or more conventionally it would be Q1 minus Q2 minus Q3 equals demand, and that would be the continuity equation for that junction. So if there's no demand, if its value is 0, it just says that inflows equal the outflows in a junction. And if value is not 0, that statement is still true. It's just the demand has become part of the outflow portion of that balance equation. If water is inserted or injected into a network, the demand is considered negative. They don't use a different letter of the alphabet usually. And all these are related within a pipe between two locations, so you can think of 1 and 2 as being two junctions by the energy equation. And the energy equation, if you recall from fluid mechanics, looks something like this. It looks suspiciously like the Bernoulli equation, because it is. It's also known as the modified Bernoulli equation. Modified in the sense that we're considering energy added from pumps, energy extracted by a turbine, and energy lost due to friction. So reading the equation from left to right, we have P1 over rho g. That term right there is called the pressure head. And the pressure divided by the specific weight of water has dimensionality of length. So that's the pressure head, and it corresponds to the amount of total head at that location that is attributed to whatever pressure the water has. The next term, V1 squared over 2g, is the velocity head. And we have this alpha alpha term here called an energy correction coefficient. In observation, they range in numerical value from 1 to 2, closer to 1 in most instances, and so we normally just treat them as 1 and don't worry about them. They're not particularly the easiest thing to measure anyway. So these alphas are going to be replaced by the number 1. So we have velocity head at location 1. And then the last term, z1, is the elevation of the point of interest. So think of that as the elevation from the datum to the center line of the pipe that we're talking about. This group of 3 terms, taken collectively, is called the total head. And it goes by a few different acronyms. TDH for total dynamic head, or just plain capital H for a total head, or TH, or pretty much any letter of the alphabet that you want to use, as long as you clarify that. The next term is H sub P, which represents energy supplied by a pump located between points 1 and points 2. And we will have a whole entire lesson on pumps coming up. P2, V2 squared over 2G, and Z2 represent the pressure head, the velocity head, and the elevation head at point number 2, respectively. And the combination of 3, when they're added together, is the total dynamic head at point 2. H sub T is head that's removed from the system by a turbine, and H sub L is head that's removed from the system by friction. So that is a compact representation of the modified Bernoulli equation for a pipeline system. And we'll see this equation again in open channels. The terms have the same conceptual meaning, but they're defined slightly differently because they're defined relative to the location of the bottom of the channel. But that's later on. So here's a diagram depicting an instance where water is being lifted from reservoir 1 and discharged up here into reservoir 2. And it passes in through this pipe, goes through a pump, exits the pump, and continues on its merry way until it gets to reservoir number 2. So the head loss going from position 1 to the suction side of the pump, or essentially the head loss along this fat purple path, is one of the head loss terms. And then the energy, or the head, when it gets to the pump, is down here. So this energy line, it has slope because there's energy loss along the way. So the total head starts at the pool elevation of the reservoir and declines as it makes its way to the pump. Then when it gets to the pump, a certain amount of head is added, which is depicted by this red line segment here. And now the energy line is up here, and then it declines as it makes its merry path to the outlet. The water is actually contained in this purple area. And so the distance from this point where the cursor is down to the reference elevation, the datum, is the elevation head at that point. And then the distance the water would rise into a vertical pipe, if there were a pipe piercing the pipeline, is this distance here, and that's called the pressure head. And then because the water is moving, it has a little additional head, the velocity head, and that's how we get from the hydraulic grade line, which is the position where water would rise in a bunch of pipes that were attached to this pipeline, or if you could visualize a slot going all the way up to the moon, that's where the water would appear. That line is the hydraulic grade line. So it locates where the water surface would be if the water could have a surface. And then the energy grade line is the hydraulic grade line plus the velocity head at any point. So the energy loss is influenced by both hydraulic and by geometric properties. So the hydraulic properties that play a role in energy loss are the material that the pipe is made out of, usually reflected in its roughness coefficient, any components in the system, valves, bends, T's, other letters of the alphabet, and the overall operating pressure or operating head. The other main component that I suppose is embedded in this operating pressure bullet is how fast the water is moving through the pipes. The geometric properties that play an important role are how long the section is and the cross section, both its shape and its area. So the pipes are usually circles, and so the area is directly proportional to the square of the diameter. And so the design variables we are concerned with ultimately are how long is the pipe, and we don't have a huge amount of flexibility because we are trying to bring water from one location to another, and it's got to have non-zero length to do that, and the diameter. And the other thing we have control over is material selection, the choice, and the kinds of components that we put in to control our system. So we can't realistically design and build a system that doesn't have valves and bends and T's, but we can design and build a system that has just the ones we need or low head loss ones as necessary to try to maintain the energy. The hydraulic grade line is a line that represents the profile of the water flowing in a partially full pipe, and if the pipe is under pressure, as is depicted here in the diagram, then the hydraulic grade line rises to the point where a free surface would exist if there were a piezometer, vertical pipe, open to the atmosphere, installed into the pipeline. So in this diagram, at the left point, there's a certain elevation. We'll just use the bottom of the drawing as the datum. So the distance from the bottom of the drawing to the center of the pipeline is the elevation head at that point. And then the distance from the center of the pipeline to the water surface in this piezometer is the pressure head at that point. And then if we know the velocity head, the distance from the hydraulic grade line to the energy grade line is that velocity head. If we move to this point, which is more downstream, and this pipe is sloped, the distance from the datum to the center is the elevation head, and the distance from the center to where water would rise in the piezometer, if there were a piezometer, is the pressure head, and then the distance from the hydraulic grade line to the energy grade line is given by velocity head. And we could actually measure that if we were willing to put a pitot tube into our pipeline. And in real pipelines, that's probably almost never done. Certainly not in water distribution pipelines. We do them in fluid mechanics labs sometimes. And so this pitot tube is sampling roughly the same location that the piezometer is sampling. And because the water's moving, the velocity head stagnates and provides a little extra elevation here in the pitot tube, and difference between that height and the height in the static tube in the piezometer is the velocity head. So velocity head can be measured, the alphas can't, but it's not routinely done. Certainly not in a water pipeline. The energy grade line is simply the line that represents the elevation of energy head of water in a water flowing in a conduit. It's the sum of the elevation head, the pressure head, and the velocity head at a location. It's going to run parallel to the hydraulic grade line and probably take the same slope as the hydraulic grade line, but it's going to be a distance v squared over 2g above the hydraulic grade line. And here's an example of hydraulic grade lines and energy grade lines in a turbine system. So the source of energy for the turbine is this high reservoir. So the pool elevation is up here, and it discharges through a turbine into this low reservoir known as the tailwater or the tail race. This pipe here is usually called a penstock, and that takes the water from the supply reservoir to the turbine, which then exhausts the water into the tailwater. Usually the penstocks are pretty large diameter because the goal is to keep the velocities kind of low. There's no, at least with the type of turbine here, this is a reaction turbine, there's no convenient way to extract energy from high velocities. It can't be zero, the water has to move. So the pipelines are usually fairly large diameter. And here the engineer has drawn the energy grade line as it moves toward the turbine. It can't be horizontal because there are frictional losses in the system, so it slopes downward. At fairly low velocity head, the hydraulic grade line is immediately below that at a distance of v squared over 2g away from the energy grade line. We go to some arbitrary point. In this example, the pool elevation is used as the reference elevation, and so the elevation head up to the center point of the pipeline where the cursor is Z, and then moving from the cursor up into a piezometer, imaginary piezometer if there were one there, the water would rise to this level. There's the pressure head, and then there would be a little bit of extra velocity head. And then when we get to the turbine, they're designed to extract all that energy, which we have preciously maintained almost to the same height as the upstream pool, extracts all that energy and has enough left for the water to flow out into the tailwater. And energy grade lines and hydraulic grade lines have a couple of practical uses. One of them, probably less practical, is given an energy grade line and a hydraulic grade line, but not much information about what the hydraulic system is, you can infer changes in slope, changes in diameter, and various hydraulic components that are installed in a pipeline system from knowing what the energy grade line is. A more useful application of hydraulic grade lines and energy grade lines is determining if a system is going to, if it's a drainage system, for instance, we normally design them so that we can keep the hydraulic grade line below ground. If the hydraulic grade line rises above ground, what that is an indication that if there's some way for water to get out of the system, it's going to flood. Energy grade line, similar information. There's a lot of, this entire portion of this chapter that I will point you to on energy grade lines and hydraulic grade lines. If I can find it. I hope I didn't just pass. I sure did. So the author has a couple of pages on hydraulic grade lines and energy grade lines, and some suggestions on why they're useful. And here's an interesting example where water is being allowed to go up over a hill, and we get a portion of the system where the pressure is negative. In usual practice, that's to be avoided. If it becomes too negative, get to the vapor pressure of water, then we'll get a vapor bubble in there and the system will fail. The water will stop flowing. And if we get way too low a pressure, not only will we get a vapor cavity in there, the pressures can be low enough that the surrounding air pressure and soil pressure can crush the pipe. And then you have a real problem. So moving along, there's our friend the energy equation again. And let's look at a way it can be applied. Imagine we were given the task of estimating discharge between these two reservoirs, and we were told that they're 2 miles apart, connected by a 2-foot diameter pipe, and the difference in pool elevations is 20 feet. We're also nicely told that the head loss for this system is 0.136 times the length times q squared divided by pi squared g d to the 5th power. So we ask ourselves, how would we estimate discharge? Well, the head loss for the system clearly has to be equal to the available head between the two pools. So the head loss is equal to 20 feet. So now we have the equation that 20 is equal to 0.136 times L q squared over pi squared g d to the 5th. So the next question we ask ourselves, do we know the value of L? And that would be yes, it's 2 miles, which is 10,560 feet. And do we know the value of diameter d? Also yes, it's 2. So now our problem becomes 20 equals 0.136 times 10,560 times q squared divided by pi squared g 2 to the 5th power. The only unknown in that expression is q. So we could solve directly for the discharge in that instance. We'll return to this picture in a little bit. That particular head loss model right there structurally is the same as the Darcy-Weisbach model. But there's also Hazen-Williams and Chesney-Manning. So Darcy-Weisbach, Hazen-Williams, Chesney-Manning are the 3 commonly used head loss model in pipeline systems. The first 2 are by far more used than Chesney-Manning, but the Chesney-Manning can be used. And in the Texas Water Code, it's implicit that we're using the Hazen-Williams model. Implicit in the sense that they provide specific values of Hazen-Williams loss coefficients to use in certain hydraulic calculation. If they're using those loss coefficients, they have subtly told you to use the Hazen-Williams equation. So we're going to study the Darcy-Weisbach equation anyway, because we had that in fluid mechanics. You may recall the Moody chart. We'll do a quick review of that. But in this course, it's not particularly useful. It's not useless, but it's not the tool of choice. The tool of choice is what I've labeled the Jane equations. And if we return to Robertson and Cassidy, they are called the explicit equations. And they're attributed to Swamy and Jane. And Jane was the professor, Swamy was the graduate student who did the work, so naturally they're called the Jane equations and not named after the fellow that actually did the work. So right here, explicit equations for pipe flow problems, and there's 2 categories of them. One is to predict discharge given head loss. The other is to predict diameter given head loss and discharge. And they both can be used in iterative fashion to infer unknowns that aren't in the explicit portion. So for instance, if we know diameter and we know discharge, we can compute the required head loss to make it so. And let me find the equations again. Oh, I'm now all lost in my book. I'm telling you to go read it, and I can't find my way around it. Okay, that's classic. Hazen-Williams, non-circular. Transitions. Explicit. There we go. So it appears on page 257 of this particular document. So we'll see these both again shortly. So for instance, if you were to forget or lose track of the diameter equation, you can certainly use this Swamy-Jain equation as written here and guess values for diameter and repeatedly calculate it until you recover a value of diameter that returns the correct flow rate under the correct head loss conditions. So let's continue. Here's our energy equation again. We're going to be discussing this orange circle, the head loss model. We haven't even addressed pump curves yet. That's a future lesson. Okay, and we're not going to deal with turbines very much. So we're looking at this orange circle, how to populate that. So the Darcy-Weisbach loss model for pipe loss is shown here in the presentation as the head loss due to friction is equal to a friction factor, F, multiplied by the ratio length over diameter, multiplied by the velocity head. If we study that equation, we conclude that the loss term is proportional to the length of the pipe, proportional to the square of velocity, and inversely proportional to the cross-sectional area, and directly proportional to the loss coefficient F. F itself depends on the Reynolds number, which incorporates fluid and flow properties, and depends on the roughness height, which is a consequence of the pipe material selection. So that's the input information required for using the Darcy-Weisbach equation. We need to know a flow rate. From that we can compute a Reynolds. We need to know a flow rate and a diameter. That allows us to compute the Reynolds number. We need to know how long the section of pipe is that we're interested in. And we need to know what the pipe's made out of. That gives us the ability to access the Moody chart to recover a numerical value for the friction factor F. So here's our friend the Moody chart. You had some version of this in fluid mechanics. Maybe not this exact chart. Well, actually, yes, this exact chart. Maybe not presented in this rather boring black and white presentations. If you had modern fluid mechanics text, they had all sorts of interesting colors. They had blues and oranges and greens and purples. And each color you get increased the cost of that textbook substantially. But if we just stick to boring old white paper and black ink, this is a Moody chart. So the information in the Moody chart, the left axis is the friction factor, and it's a logarithmic axis. The bottom axis is a Reynolds number, and it's also logarithmic. There's a series of a family of curves here, and they all get their information from the right axis. And so each curve represents a relative roughness or a roughness ratio, which is the roughness height of the material divided by the diameter of the pipe. And so for instance, the relative roughness 0.002 is this line right here. And you see that a portion of it is pretty much flat, horizontal, and then it starts to curve up as the Reynolds number goes down. You'll also see a portion of the chart over here that when the Reynolds number gets less than about somewhere between 2 and 5,000, we transition to a single formula which gives us the friction factor. which is 64 over the Reynolds number, up to a Reynolds number of about somewhere between 2,000 and 5,000. So on the leftmost part, that is the laminar flow region, and the laminar flow is completely determined by the Reynolds number. The friction factor is completely Reynolds number dependent. Then we get to this transitional region based on the different roughness ratios. There's a dashed line here called the fully rough line. To the right of that dashed line, the roughness ratio lines are horizontal. So at that point, the friction factor depends entirely on the material. To the left of this line and to the right of the laminar region, the lines have curvature, and in those cases, the friction factor is dependent on both the material and the Reynolds number, with a notable exception. If the pipe cloth is fully smooth, meaning its roughness ratio essentially is 0, it follows this curve down here where the cursor is going, and at that point the friction factor is entirely dependent on the Reynolds number. Okay, that should be pretty good and confusing now. The roughness heights for different materials are tabulated. In this particular example, there's a few of them tabulated directly on the chart, but we would find that information as necessary by using a Google search or something similar. So for instance, cast iron is 0.0085, and we'll have an example where we will revisit that. So the three classic examples of the Moody chart, I'm going to go through these rapidly, mostly by way of review. Here's one of them, which is to calculate head loss given discharge diameter and material. And in this case, we have the head loss is determined first by computing the Reynolds number from the discharge and the pipe diameter. Then we compute the roughness ratio from the tabulated roughness height for the selected material. And finally, we recover the friction factor from the Moody chart. So here's a simple computational example. Oil, specific gravity 0.9, viscosity 0.00003 feet squared per second, flowing in 2,000 foot long, 6-inch diameter cast iron pipe at 1 cubic feet per second, and the pipe slopes upward at 5 degrees in the direction of flow. Estimate the head loss in the pipe. So that's our task. The other question it asks is estimate the pressure drop in the pipe. If we can figure out the head loss, the pressure drop is very straightforward. So here's a sketch of what we're trying to do. So we have this pipeline, point 1 and point 2. We apply the energy equation, cancel out the common terms, and the common terms are the velocity headed at both points, and it cancels because it's a constant diameter pipe. And what we have left is pressure head at point 1 plus elevation head at point 1 is equal to pressure head at point 2, elevation head at point 2, plus the head loss. So we can rearrange this slightly to isolate the head loss term, and what we have is the change in pressure plus the change in elevation equals the head loss. And then we would calculate the head loss in the following procedure. First, we would compute the Reynolds number. We can get the Reynolds number from the flow rate by dividing by the area to convert flow rate into a velocity. So we have 4 times the 1 cubic foot per second divided by pi times the diameter, half a foot squared. So this group of terms that the cursor is circling around is the velocity. Multiply that by the diameter, d, 0.5. Divide everything by the kinematic viscosity, 0.00003 square feet per second, for a Reynolds number of roughly 85,000. The Reynolds number is greater than 10,000, so we're absolutely sure that this is turbulent flow. and then we would compute the roughness ratio by looking up the roughness height, 0.0085 from the table, and then that produces a roughness ratio of 0.0017. And now we have all we need to use the Moody chart. So we come in at 87,000 Reynolds number. We go up to the 0.0017 roughness ratio line, and at the intersection we then read directly left to the friction factor, which in this example works out to be 0.024. So now we have all the pieces to calculate the head loss, and we can just apply the Darcy-Weisbach equation correctly. So here it is in discharge form, and so the 8 and the pi squared d to the 5th q squared converts the discharge into velocity for us for circular pipe. And so now we just apply the formula 8 times 0.024, which we just looked up in the Moody chart, times 2,000, times 1 quantity squared, divided by pi squared, divided by g, divided by 0.5 raised to the 5th power, for a head loss of 38.6 feet. And in the next part, the pressure calculation is illustrated here in line 15. The change in pressure is simply we rearrange the equation, multiply by the specific weight of water, and come up with about 83 pounds per square inch. So our second example is 80-foot horizontal half-inch diameter pipe with a head loss of 40 feet. What's the discharge? In this example, we'll have to use the Moody chart somewhat iteratively. So the first thing we have is we can apply the Darcy-Weisbach expression directly, and that head loss is the change in pressure divided by rho g, and that equals 40 feet. And the reason that's true is because the pipeline's horizontal, so there's no elevation change, and it's a constant diameter, so the velocity heads will be the same at either end of it. So all that's left is pressure change. So first we would compute the roughness height ratio, which we would use ultimately to look up friction factors. In this case, the roughness height ratio works out to be 0.0036. That's going to choose a line on the Moody chart. Go back up to this one because it's closer. 0.0036. So the line's going to be somewhere in here. So that curve, it's not directly plotted, but we certainly can visually interpolate the line. And then construct a table of computations. And what we'll do is we're going to guess values for flow rate, and we'll increase them or decrease them until we get a computed head loss about the same as the stated head loss. And at that point, we would declare that we have an answer. So here's an example. We'll make a first guess of 0.001 cubic feet per second. Then we would compute a Reynolds number because we know the diameter. We know the roughness ratio, so we can look up a friction factor with this Reynolds number and that roughness ratio. We get a friction factor of 0.036 for a computed head loss of 0.57, which is quite a bit below the 40 feet. So we increase our guess to, in this case, 0.005 cubic feet per second. Reynolds number is computed. New friction factor is looked up in the Moody chart, 12 feet of head loss. Well, we're headed in the right direction, pun intended, but we need to increase it some more. So we go up to 0.008, Reynolds number, friction factor 0.031, you get 31 feet of head loss. So we increment a little bit more, 0.009, Reynolds number, friction factor 37.9. We could conceivably go up again. We're getting to the point, the friction factor is not changing very much because of our eye's inability to read the chart. So there's a certain resolution at which we can't resolve. With that, as the Reynolds number moves a little bit, there's no apparent change in friction factor, which is likely not true, but that's a limitation of the chart. So we would conclude the pipe discharge is around 0.009 cubic feet per second. It's going to be a little bigger than that, but it may only be bigger a few more places after the third digit in this case. So the last example is diameter given discharge head loss in material. So this is really the design use of the MOODY chart. And here we have 600-foot iron pipe to carry water at 3 cubic feet per second. We have 60 foot of elevation change, and we want the pressure drop to be 6 feet ahead. What diameter should we choose? And so in this case, we would set up the problem almost identical to the one we just did. And then instead of guessing discharge, we're going to guess diameters. The added complication of that is that every time we change diameter, the computation for Reynolds number changes and the computation for roughness ratio changes. But it's the same idea. So we guess the diameter, compute a Reynolds number based on that diameter, determine the roughness ratio based on that diameter, go to the MOODY chart, look up the corresponding friction factor, apply that friction factor in the head loss equation to get a computed head loss, which in its first line is 2,500, which is quite a bit larger than the required 66. So we'll increase the diameter, recompute the Reynolds number, recompute the roughness ratio, look up the friction factor again, and compute a new head loss of 69 feet. That's pretty close. We make the diameter bigger yet again, but not by much, about 5% bigger. Compute the new Reynolds number, compute a roughness ratio, look up a friction factor, and here's a good instance. The friction factors in the table don't change, and that reflects our inability to see the difference between 7.06 times 10 to the fifth and 6.92 times 10 to the fifth on this chart. If you look at the spacing here, those are essentially the same number on that chart. It also reflects our inability to resolve the difference between a roughness ratio of 0.003 and 0.0029. But if we go forward with the calculations, we get 63 feet of head loss. And so the result after 3 tries is that the diameter is somewhere between 6 and 7 inches. For what it's worth, there's actually commercially available 7-inch pipe. I imagine it's not very common, but it does exist, or at least it existed at the time this document was created. And so one could specify that size in such a situation. It would have to be, you'd have to really want that pipe. The 7-inch is pretty unusual. The alternative to the MOODY chart are direct or explicit equations. And so I showed you in the chapter 5 of Robertson, the section that discusses these equations. And here they are repeated in the presentation document. And we'll skip the programming of them. If you want to see a little example of that, you can watch the morning lesson. But we will go to the class server. So you look at those, and looking at those, oh, that's pretty easy. I don't need to program anything. But if you were to do that in a hand calculator, it wouldn't take you long to conclude, I got a whole lot of buttons to press. That gives me a whole lot of opportunities to make a transcription error. So this is the kind of thing that when we want to encode into some computational tool. And for this class, such a tool exists, yay us, called Q given head loss, and there's the URL. So in the PDF, that's not linkable, but we can get to it this way. Go to the web-based toolkit, choose pipeline hydraulics, and what we want is discharge given head loss in US customary or SI units, web-based calculator to approximate discharge in a pressure conduit using Swami James. So we'll click on that doodle there, and we have the required input that's prompted for us. So let's go ahead and revisit the example 2, discharge given head loss. So we'll go ahead and put that information in and see what it computes. When we did it essentially by hand, we got discharge of 0.009. So I haven't necessarily tested it for today, so it's quite likely I could do something wrong, but let's see the advantage of having our own home-built online calculator. So the diameter of our pipe is 1/2 inch. That would be 0.5 feet. No, that's 6 inches. 1/2 inch is, rats, I need a calculator. I can't do that in my head. Okay, so there is my diameter. Okay, and gravitational acceleration, we'll do it in US customary units. Head loss. So our working head loss is 40 feet. Pipe length was 80. Roughness value for the pipe, we'd still have to look that up. 3 zeros and a 1 5. And the kinematic viscosity, I hope that's here somewhere, otherwise I'm going to have to do it from memory. I'm going to have to do it from memory, which I don't have to do it from memory. I can create a new tab. We'll go to the same tool and have a fluid mechanics tool, properties of water, assume it's at 50 degrees Fahrenheit. Our kinematic viscosity is 1.41 times 10 to the minus fifth. And we get a discharge of 0.0087 compared to 0.009. Now, essentially the same result. And I would argue that for doing a 1 of, it doesn't matter, but if I had to do that 10 or 15 times, I think I would prefer the online computer document. And all it does is implement this equation. But it only gives us 6 ways to make a mistake, instead of all the square roots and squaring and logs of stuff to make a mistake. And so we basically have just worked through the online tool, a big blue blank space, and we move on to the next one, the Hazen-Williams equation. So the Hazen-Williams loss model, expressed as a head loss model as shown here, is head loss is equal to some coefficient, so that 3.02 changes value depending on whether it's US customary or SI units. I'm pretty sure I wrote it for US customary in this document. 3.02 times the length times the diameter to the minus 1.167 power times velocity over a thing called a Hazen-Williams loss coefficient, C sub h, quantity raised to the 1.85 power. So if we examine this expression, we conclude that this particular model has frictional loss proportional to length, just like Darcy Weisbach did, proportional to velocity raised to a power, not squared this time, but to the 1.8 power. So 1.8 is almost 2, so they're pretty close in that respect. They're certainly both superlinear. and it's inversely proportional to a cross-section area expressed as a hydraulic radius. Here we're showing it as diameter, and we'll explain that shortly. And the loss coefficient depends on pipe material and finish. And one thing different about this is that this loss model is intended for turbulent flow water only. So the application of Hayes and Williams to a liquid other than water is fundamentally incorrect. As a velocity form, here's the head loss equation, and here's the same equation written in discharge form, so we can enter discharge instead of velocities. And so all we need to use this is discharge, length, diameter, and the C sub h coefficient. The C sub h coefficients are tabulated in tables that look something like this. There's certainly more than the table here. There's many more tables, so imagine there'd be hundreds and hundreds of rows for just about any imaginable material that's ever actually been built. And so you see the numbers are numbers like 130, 140. We get to corrugated, it's like 60, and brick. Well, brick sewer is higher than I would have expected, 90. So as the number goes up, it's reflecting lower head loss conditions. So high number means smooth, low number means rough. So in the Hayes and Williams model, the frictional losses increase with decreasing value of the Hayes and Williams coefficient, decreasing numerical value. So here's an example. First we'll do it by hand, we'll do it again on the computer model. Estimate the head loss in a 72-inch, 10,000 foot steel pipe that carries water at 200 cubic feet per second using the Hayes and Williams formula. So this is quite simple. We just simply put the numbers in the formula, perform the indicated arithmetic, and we get 28 feet of head loss. Do that once, no big deal. If I have to do it a dozen times, I would want to use something that helps me. And so I might use this tool here, which takes the same information and produces the same results. If we want to go look at head loss C factors, here's a table from one potential internet source. And there's other ones there. And it describes a little bit how you could use the Hayes and Williams formula. So let's repeat the example there. Let's see, head loss coefficient of 100. Easy. Diameter was 72 inches, so that's 6 of those feet. The length was 10,000 feet. And the value for discharge was given was 200, right? 200. Then go ahead and do the computations, and it comes up with 27.5 feet of head loss. Pretty close to 28, I would argue it's, for all practical purposes, it's the same number. And it should be. It's implementing these same equations. If we go back, there's a variant for SI units, and what changes in the SI variant is that coefficient right there, and that produces a different number out front. And this is used in the same manner. It should be fairly straightforward. You can simply enter the numbers into the input interface. So the Hayes and Williams is usually presented as a velocity equation. If you were to type Hayes and Williams model in Google, the first few thousand it would come up with would be this expression. And it has this term R in it, which is called the hydraulic radius. And what I did to turn it into a head loss model is I isolated the slope, because that's head loss per unit length. Messed with the exponents to get the exponent to 1, and then rearranged the velocity into it. And that's how the head loss version comes comes about. The hydraulic radius, by definition, is the ratio of cross-sectional flow area to the wetted perimeter in a circular pipe that's full, so it has no free surface. The area is this green part here, that's pi d squared over 4, and the perimeter is pi times the diameter. And that's represented by this red path here. And it's the ratio of those two is the hydraulic radius. And it turns out that for a circular pipe that's full, the result is the geometric diameter divided by 4 is the hydraulic radius. And so that's what's used in the discharge form of the Hayes-Williams formula that I presented earlier. Lastly, the Chezy-Manning loss formula is Manning's equation rearranged as a head loss formula. And here the same thing happened. The Manning's equation, if you recall from your hydrology class, is velocity was 1.49 over Manning's n times r to the 2/3 power times slope to the 1/2 power. And we rearrange that, we get slope to the 1/2 power equals everything else, and then we square that, and that gives us slope is equal to something. Then we recall that slope is head loss per unit length, multiply both sides by length. And when we're done, we have this. Head loss due to friction is the length multiplied by n squared, which is Manning's loss coefficient, velocity squared over r to the 4/3 power. So again, the loss is proportional to length, proportional to the square of velocity, and inversely proportional to cross-sectional area expressed as hydraulic radius. This constant 2.22 will change depending on whether you're using US customary or SI, because that initial coefficient, the 1.49, changes to 1 for SI. The loss coefficient depends upon the material in the finish. And to find those loss coefficients, I don't have a Manning's calculator prepared, but I do have a Manning's N database. Here's what Manning's N databases look at like. They are descriptive. So if we were looking at, I don't have any pipe descriptions in here, but if we were to do smooth mortar, sand, straight alignment, no other information, the Manning's N would be 0.011 in the database lookup. And there's also printed tabulations that are probably far more useful for using it in a pipe flow context. The next topic I want to refresh your memory is in fitting losses. They're also called minor losses. So fittings, joints, elbows, inlets, wells, outlets, bends cause additional head loss in a pipeline system. They picked up the name minor loss not because of the magnitude, but because they occur over short distances. And the typical minor loss model is the minor head loss is equal to a constant K called the minor loss coefficient. And the minor loss coefficients are tabulated for each type of fitting, joint, elbow, inlet, outlet, weld, multiplied by the velocity head in that device. If the device is a device that changes diameter, so a reducer, for instance, you compute the velocity head using the smaller diameter. The loss coefficients themselves are tabulated in tables very much like the Hayes-Williams coefficient, different tables, of course. And here's some examples. The typical magnitudes are like those expressed here, a little bigger than 0. As far as I can recall, I don't recall double-digit results, so you won't get a 22. You might, but I don't think that's very common. So here's an example that illustrates a fitting loss model. So what's the pressure drop across a valve with a nominal diameter of 8 centimeters, loss coefficient of 3.2, and a flow rate of 0.4 cubic meters per second. So to solve that, we would first write the minor loss equation and then solve for the head loss. In this case, it's just direct application of the equation, and we get a head loss of 10 meters. Then we would convert the head loss into pressure drop simply by multiplying that head loss by the specific weight of water, which is 9,800 newtons per meter cubed, at least for really cold water, times 10.3 meters of head loss for 101,300 pascals of pressure change, or 101 kilopascals. And if you recall, 101 kilopascals is pretty much 1 atmosphere. So this particular example, that valve, that flow rate produces almost 1 atmosphere of pressure drop, which is a lot. Well, maybe not. It's a lot if we don't want that kind of pressure drop. So to conclude today, we'll return to this diagram, and we now have all the pieces of a loss model to examine. So talking about everything in orange. So the pipeline losses, for example, the Darcy-Weisbach one, express the loss on these orange paths in the 2 pipes. So length 1 plus length 2. And if the diameters change, we can account for that. And then we have the minor losses, in this case for this inlet, this bend, and this exit. We look those up in tables. So we sum all the minor losses, we sum all the pipeline losses, we add those 2 sums together, and that becomes the head loss model for the hydraulic system, or at least for this one that's depicted here. So coming up next meeting will be, I'm pretty sure pumps is next, so we will deal with the purple circle in our next lesson. Looking back at the course, in the exercise category, we have 1 and 2, which are working on in demand. So we don't, the application of head loss models is not due until the 24th. So what we talked about today is directly applicable to that. But I think you want to wait until we do pumps before you attempt exercise set 4. It's not very hard. In fact, you probably could have had it in fluid mechanics and pretty much done it. So that's all we have on exercises. I will be creating and putting a quiz up sometime over the weekend, but there'll be a week from when I post it to when it's due, so there'll be plenty of time to take the quiz, and it will be a multiple attempt quiz, so you can take it once and see what it is, and then take it a second time for record. Are there any questions before I end the recording and the call? We got 6 minutes left. I didn't expect it to take that long, but I guess I was talking slower than I usually do.
So for the contour map for the homework,
yeah.
Do you want that on a like? How do you want that to be done?
What do you mean by how do I want it to be done?
Do you want us to scan it on our phones, like do it on a piece of paper and scan it on our phone?
how to turn it in, you mean?
Yes, sorry, my bad.
Oh, okay. I would suggest you produce a completed map in the text file as a PDF file, and then just upload that to the Blackboard.
Okay, thank you.
Okay.
So you don't want a sheet for each question, correct?
I don't need a sheet for each question. You can compact it. If this were a live face-to-face class, I would demand a sheet for each question, but there's no point.
Yeah, I figured that when I was doing it in Civil 3D, but I don't know. I gave you a sheet anyway for each thing, and it was repetitive.
Well, it doesn't really, it's not going to hurt anything. That's the beauty of electronic documents. It doesn't really matter how long they are because you can scroll through them pretty quick. But human beings can't read them very quick. Any other questions? Okay, good. Well, have a good evening, everybody. Have a safe weekend. And the university president encouraged us not to travel and go and get infected this weekend. So I would admonish you to follow his guidance so we don't have to shut down the university again. And be as safe as you can. Don't get infected. I'll see you Tuesday. And have as good a weekend as you can under those restrictions. So,
yes, sir. Have a good weekend, too. Thank you.
Bye-bye.